Good morning. Can you hear me?
Morning.
So today it's 9:30. We'll get started. Today we're dealing with module 12. So let's take a look at where we're at here. Okay. I had to use a different browser this morning, so I'm hoping things will work okay. I couldn't open Google Chrome for some reason. All right. Just trying to get it here into module 12 for some reason. Okay, yeah, it's better. Okay, so just getting into, first of all, orbitals. And when we talk about orbitals, all we're really talking about are volumes of space where we can find certain kinds of electrons. And this is somewhat related to what we were dealing with. Let me see what's going on here. It looks like that's come out in a different page for some reason, but anyway, all right. If you'll remember, let's say we've got something like fluorine. And fluorine has 9 electrons. That's awful. Let's try that. All right. For some reason, my computer gets slow again today, and I'm having trouble even drawing a circle here. All right, that's better. Okay, that's got 2 electrons in the first level, and then we've got 7 electrons in the second level. And we know that this matches pretty much what we see on the periodic table. And I'll show you what I mean by that. So let's look at again at soft chalk. I'm just going to, yes, if you look at the periodic table here, you look where fluorine is. What I've done is I've moved the helium over to next to the hydrogen, even though usually we express it as being on top over here with neon, but I did this for a specific purpose. And you can see that there's 2 electrons or 2 atoms in the first row, and then we count 1, 2, 3, 4, 5, 6, 7 on fluorine in the second row. And then if we're going to go to the third row, we'd go 8, and then we go as many electrons across as we want to go. So what we're looking at here in the first row, we've got the, you know what, I'm going to have to stop the share here for a second and cancel some processes here that seem to be annoying me a bit. Let's get rid of that one. All right, we'll see if that helps. There's nothing else here that's really. All right. I will also close down my paint program here and restart it. Hopefully that'll fix the problem. Okay. Let's see if that helps or not. Doesn't really. And I just did a restart too before I got into the session here. It's quite frustrating today. Oh, geez. Dear. All right. I'm going to have to go back to the other profile here, see if I can shut some more stuff down. I think it's Adobe that's the problem. It's always Adobe that's the problem. I don't know if I told you this, but I really hate Adobe. Jeez, come on. There we go, that's better. All right, I think we're speeding up now. All right. So this is fluorine that we're talking about here. That's better. And in the middle, we've got 1s2, and the 1 here indicates that first row. And here we've got an actual mixture of 2s2 and 2p, will be 2p5 really. So the 2 here indicates this second row. And in the third row, we have the possibility of 2s, 3p, and 3d as well. So when we're looking at the shapes of these orbitals, you can see the S is kind of like a spherical shape and the P is like a dumbbell shape. But there's 3 of them.
You don't see anything.
You don't see anything?
I'm not seeing anything.
You don't see anything? I'm
No.
sorry. Maybe I didn't. Maybe I meant. Sorry, I meant to go back to sharing and I didn't. Sorry. Thanks for letting me know. Now you should be able to see something.
Yeah.
Thanks. There we go. So the 2 here is indicating the second row here. And we've got 2s and we've got 2p. So the S is spherical and the P is dumbbell shaped over here. Now there's 2 electrons per orbital, and if you count, we've got 2 columns here for the S. So that would indicate 1 S orbital, so 1 S line here, with each electron representing effectively an element. You'll notice that the electrons are always going to be oppositely directed when they're in the same orbital. So if one's up, the other one will be down. So we've got 1s2, that's going to be the first row, and then we move down here and that's going to be 2s, and you see this whole thing is the S block. This is the P block over here, and you'll notice there's six columns here, which means there's 6 elements, which means there's 3 orbitals because we can put 2 electrons in each orbital. And each of these orbitals has a slightly different orientation, one along the x-axis, one along the y-axis, one along the z-axis. The d orbitals get even more complicated than that. We have 10 elements in the d block, which means there's 5 d orbitals. And in the f block, we've got 14, which would indicate that there are 7 orbitals. Okay. So how do we assign electron configurations then? Well, it's actually not difficult. I like to just go ahead and do it by reading from left to right across the periodic table. So let's look at an example. We'll do it for chlorine here. Look where chlorine is on the periodic table. You see it's at 17. And what that means is we start out and we do 1s2. Yes, my computer's sped up now a bit. I think it was Adobe that was the problem. So 1s2. And then we've got 2s2. And then we've got 2p6. So I'm just reading across the table here. And at this point, we'd be at neon. And you'll notice if you count these, you've got 2 plus 2 plus 6 is 10, which amounts to neon here. Now we're going down to chlorine, which means that now we're looking at this level, which is 3s2. And then we go across 1, 2, 3, 4, 5. That'll be chlorine. That'll be 3p5. And what we'll learn about when we get to, I think it must be test 3, we'll do quantum mechanics, and we'll learn a little bit more about what possible numbers we can have here in front and why we have those numbers in front. But one thing that's sort of a constant here, it really helps, is we know that S will start at 1s. And P starts at 2p. D starts at 3d. And F starts at 4f. So I already told you that with the D, there's 10 elements, which means there's 5 orbitals. And it's impossible to fit those 5 orbitals in the first, anywhere in the first 2 rows. So that's why it starts at the 3rd row. Remember, this would be the first 2 rows here that we're looking at for fluorine that I'm showing you up here in this diagram. So we need at least another row here in order to get D orbitals in. And F's the biggest still, or need more room still, so they have to start at the 4. So the effect of that is we just read left to right across the periodic table and then start at each of these individual things. It's not too hard to remember: S starting at 1, P starting at 2, D starting at 3, and F starting at 4. Anybody got any questions so far? But what if we had something a little bit more complicated? Let's say we wanted to do RE, right? So RE is much further down on the periodic table. So let's look at how we would deal with that. RE is at 75, which is down here in the D block. So when we're doing that, we would do 1s2, 2s2, 2p6, which would leave us here at neon, and then 3s2 and 3p6, which puts us here at argon, which is 18. You can see that in the periodic table up here. Next is 4s2. You notice we just keep on adding 1 for the s's here. And then we go across 4s2, which is here. And then the next thing is you have to start at 3d10. So D start at 3. I know that seems a bit incongruous because we just got to 4s down here and now we're doing 3d. And we're still going here across 4p6. So that would leave us at krypton at this point. Does anybody have any questions so far? The next one then is 5s2, which is puts us here at strontium, and then 4d10, and 5p6. So again, I've just gone 1 more on the p's here. That puts me at xenon, which is at 54. Now I'll go to the next one, that's 6s2. Now at 6s2, you'll notice, and it's probably a bit easier to see down here, you'll notice that's where we're at now, is 6s2, which is going to be barium. And you'll see that it jumps down here into the 4f. So the 4f actually starts here at 57 and then goes across. So if we go 4f, and that's going to be 14, then it comes back to 5d, and it'll be 5d 1, 2, 3, 4, 5. And that would be the total electron configuration for RE. I wanted to do that example to show you how it jumps down into the F block and then jumps back up again. Does anybody have any questions? All right. But we know that writing out all this all the time can be a little bit annoying. So we can shorten this down and we can do what's called an abbreviated form. of the electron configuration. This is what I would call a full form right here. And what we can do is we go backwards to the nearest noble gas. So the nearest noble gas to Re, back from it, would be 54, which is Xe. So what we can do is we can just put in Xe, which covers the first 54 electrons, which happens to be up to this point here. If I added all this up, it would come out to 54. So up to 5p6. If you don't believe me, it goes 2p, 3p, 4p, 5p. So that's where we're at. All of that would be 54. And then 6s2, 4f14, and then 5d5. So that would be the abbreviated form. Does anybody have any questions? So it's not too bad. Okay. The next one is to draw the atomic energy diagram for something like N. So I don't like to do this for very, very big elements. Anything up to 20, I think we can probably deal with. And you'll see that what I've done here is laid this out by orbitals. So we've got 1s, 2s, 2p, 3s, and I'm coming down here because I'm running out of room. That'll be 3p, and then 4s. Now if we've got nitrogen, nitrogen comes out to be 7. And that would be 1s2, 2s2, 2p3. And where I'm getting the 7 from, let's go back to the periodic table here. Nitrogen here is in the second row, and it's in the third position in the second level, which is the 2p level right here. And there's 3 of them there. So when we're putting the electrons in, we'd put 2 in the first level, and they have to be in opposite directions. So we put 2 in the next orbital here. But now that we've got 3 orbitals that are the same energy, I have to put them in one at a time. So going from the bottom to the top, that's called the Aufbau principle. And then once we get to orbitals that have the same energy, these ones here, we call that Hund's rule, which states that the electrons have to go in one at a time. So this, what I'm doing here is only something we do for the lower ones because it would be too annoying to do it for the much higher ones. But we can do anything pretty much up to 20, I think, pretty easily. And we've just followed that same rule for putting in the electrons. And that will determine then how many unpaired electrons we have in our final element as well. So for this one, there would be 3. There would be 3 unpaired electrons. They're the ones that are single right here. So that would be for nitrogen. Let's just do sulfur for kicks. Be 1s2, 2s2, 2p6, 3s2, and sulfur here would be over 4, so it'd be 3p4. So that would be for nitrogen. And I'm just going to continue on here. We'll put in the rest of those electrons. That'd be 2p6, 3s2, and then we need to put in 4 more electrons here for sulfur. 1, 2, 3, because those are the same energy, and then 1 more in here. That would be sulfur. All right, and that would have how many unpaired electrons? Have 2 unpaired electrons. Does anybody have any questions?
So what happens if we do anything more than 20?
Well, I mean, you could. I'm just saying that I wouldn't ask you to do more than 20, Michael.
Okay.
It would just mean that we'd have to obviously have more lines and more arrows, right?
Yeah.
But the concept is exactly the same. I just don't see any point in going higher than 20 to illustrate the concept of Hund's rule and the Aufbau principle.
Thank you.
All right. So that's what we were just talking about with the unpaired electrons. Now, identifying an element based off its electron configuration is pretty easy. If you wanted to do Kr5s243, all you would need to do, I'll go back to the first page here. What you do is you find out the atomic number of Kr, which in this case is 36. And 36 plus 2 is 38 plus 3 is 41. So then you would just find 41 on the periodic table. And 41 on the periodic table is here NB. So that's how you do it. It's pretty easy to identify an element based off a electron configuration. It's just counting up those electrons. Anybody have any questions? Okay. This won't be on the test. But it's something that you'll see in the homework, and I want you to at least have the experience of seeing it. And this is oxidation states. Now, oxidation states are essentially charges. That's really all it is, just a charge. And there's certain things that we know the charges for, and certain things that can have different numbers of charges. We've kind of been through this when we went through module 5 back in test 1, and we were talking about type 2 elements. Well, we can extend this out to other elements as well. But if we go with the assumption that group 1 will always be a 1+ charge, group 2 will always be a 2+ charge, and then add to that that oxygen is going to be -2 charge, then we can find the charges of certain other elements that are in compounds, for example, like CaSO3, and we're looking here for the oxidation state or the charge of sulfur. So the other rule that we have here is that all the oxidation numbers add up to the charge on the compound. And when you've got CaSO3, you can see that there's no charge on it because it's completely neutral. And the reason we know there's no charge on it is because you don't see any superscripts here. I'll do an example of something that's got a charge on in a second, but in this case, the charge is 0. So it's just a little bit of algebra. So it's going to be Ca plus S plus 3 times oxygen is all going to add up to 0. That's an O, not a 0, that I'm trying to draw there. So if we look at the charges, calcium's in group 2, sulfur is what we're looking for, and then oxygen, see that's a -2 charge. It's not an O, it's not a 0, it's an O, and that adds up to 0. I'll make that a 0 with a line through it. And the 2, so that means that we can just solve for S now, and sulfur is going to equal, in this case, so it'd be 2, and it'd be minus 2, and then -2 and -6, that's 4. So sulfur would have to be 4 here, and that would be the oxidation state. So that's kind of like the charge on sulfur, if you will. Does anybody have any questions? So it's just a little bit of algebra that has to be done here. I'll skip down to this one, CrO42 minus, because that one has a charge on it. I want to show you one with a charge. And what we're looking for here is the oxidation state of chromium, Cr. So it'd be Cr plus 4 times -2, that's for the oxygen, and all that adds up to -2. So the chromium then is equal to 6, and that would be the oxidation state or the effective charge on chromium. Does anybody have any questions about oxidation states?
So for the CR, how did we get 6?
Well, if you look, see how it's CR minus 8, right? -2 plus 8 would be 6. You know, just by moving the 8 over the other side, Michael.
Okay.
So we're
Thank you.
just doing a little algebra, all right?
Yeah.
All right, so we're going to also look at Lewis structures. When I'm doing Lewis structures, I kind of like to just stick to 2 kinds of rules here. Hydrogen needs 2 electrons. Because it wants to be like helium, and everything else needs 8 electrons. Or at least wants 8 electrons. So this underpins everything that we're doing here. The other thing that's really important is that we must use the exact number of valence electrons that we calculate. Now, if you think about what valence electrons are the electrons in the outer energy levels. And those are the only ones that can really be involved in bonding. So when we're dealing with, say, something like, we'll say sodium, might not be the best example. We'll do sodium though. Sodium, it has an atomic number of 11. So it's got 2 electrons in the first row, 10 in the second row, and 1 in the third row. And that would be the valence electron. And that's typically the only one that's involved in bonding. So how do we determine valence electrons for any element? Well, it's pretty easy. All we need to do is look at the periodic table. And we've done this before back in, I guess it was module 1 or module 2, or both of them actually, I think. And if you look at the groupings on the periodic table, it goes 1, 2, and then over here to 3, 4, 5, 6, 7, 8. And those numbers, those column numbers are often written above, and sometimes they are, sometimes they aren't, but you should be able to know what those column numbers are, and that actually tells you how many valence electrons there are in that group. So we'll be always sort of referencing back to that to get the number of valence electrons. And we have to use that exact number of valence electrons when we're doing a Lewis structure. So when so go back to, come on. Having a little bit of trouble here enlarging this. Let's try it again. There we go. So let's say you were asked to draw the Lewis dot structure for CH4. What you'd need to do is calculate the number of valence electrons. And the valence electrons for CH4 would be 4 times 1 plus 1 times 4. So let me show you where I'm getting those numbers from. If we go back to the periodic table, you can see that carbon, you'll see carbon is in group 4. Carbon's up here, it's in group 4, and hydrogen is in group 1. there's one carbon, so it's 4 times 1, and then 4 hydrogens, so it's 1 times 4. That total would be 8. So we've got 8 electrons that we must use. And we're trying to, again, hydrogen needs 2 electrons, but everything else wants 8, and that's what we're going with here. When we're expressing electrons, I like to express them as lines, and that would be 2 lines represents an electron. So what I like to say is that that line is equal to 2 electrons in between. So if we were to show the CH4, we could put the hydrogens on the outside first and then put lines to them. And lo and behold, we've already used up our 8 valence electrons. So that would be a completed Lewis structure for CH4. So carbon already has 8 and all the hydrogens have 2, and that's as far as we need to go with that. So let's look at something a little bit more complicated. What about something like SO3? So SO3, the number of valence electrons is equal to 6 plus 3 times 6, which is going to be equal to 24. And then what you would do is figure out where the electrons go. So the first thing you would do is put the S in the middle and 3 oxygens on the outside. Then you'd put a bond from the sulfur to each oxygen. Remember, our goal here is to use 24. At the present time, we've used 6 electrons. Does anybody have any questions so far? The next thing we want to do is we want to make the oxygens happy by putting another 6 electrons around them to give the oxygens 8. Remember, this is because everything wants 8 electrons except hydrogen. Now, if I do that, then I have used a total of 24. The problem is that sulfur has only 6 electrons around it. So I have no choice now but to take 2 electrons and have them shared between one of the oxygens and the sulfur and create what's known as a double bond. And this is often the most confusing thing for students because they're always wondering, well, when do you do a double bond and when don't you do a double bond? Well, if you've used up all your electrons and something's still unhappy, the central element we're talking about, if the central element is still unhappy, then you need a double bond. That's how it goes. It won't always be that way. Sometimes the central element will be happy and you can just stop. But other times, like this one, we've used up all 24, but we now need to create a double bond so we can have that sulfur be happy with 8 electrons and the oxygen be happy with 8 electrons as well. Does anybody have any questions? Now, when I'm asking questions about this, I ask two kinds of questions. I can ask, how many double bonds? And that would be, in this case, 0. And the other thing I can ask is how many non-bonding electron pairs or lone pairs? Now, non-bonding electron pairs are exactly what it says. They're electron pairs that don't bond. So how many non-bonding electron pairs, also called lone pairs? We've got 1, 2, 3, 4, 5, 6, 7, 8. So this would be 8 non-bonding electron pairs or lone pairs. Does anybody have any questions about counting non-bonding electron pairs or lone pairs?
How'd you get 0 double bonds?
Oh, sorry, it should be 1. I don't know why I put 0. I apologize for that.
Okay, thank you.
Yeah, you're good. Yeah, it should be 1 double bond, yeah.
So single bonds are just one line, double bonds are two lines, triple bonds are three lines, and
That's right.
you don't mix them. Okay, so it only asks for double bonds, and then you only count the double bonds. Got it.
That's right. That's right. Sometimes typically it's 0, 1, or 2, Joseph.
And for lone pairs, you count by twos, correct?
Well, because they're pairs, yes.
Yeah. Okay. What if there is a single outside?
There won't be.
Like there's.
There won't be, because your valence electrons will always be an even number, Joseph.
That's not the case for the assignment. There's one with a -1 charge.
Oh, yes, has a -1 charge, but I'm saying that the valence electrons are even.
Okay.
Okay, always. I mean, that's what we'll make it. Now, single electron species do exist, but they're fairly unstable. We tend not to talk about them very much because they're not very stable. But we won't be worrying about too many of those. So I want to point out here a fairly neat exercise, and that's this one. And it's kind of like it's a matching exercise, and it requires you to draw all of these different Lewis structures and then figure out how many double bonds there are. And what's really cool about this is there's a video that you can click on that will actually help you with that specific assignment. There's another one here that deals with non-bonding electron pairs. And again, you're required to draw all the different Lewis structures for that and match the electron pairs. That's a really cool exercise too. And again, that has a video that helps you out as well. So I really can't stress enough the importance of doing that, but so few people do. So few people, I don't know why, they just don't like doing it for some reason, but I think it's really, really useful to help with the understanding of these Lewis dot structures. So Joseph, to answer your other question, how do we deal with charges? Okay, so with charges, each negative charge adds a valence electron. And then each positive charge takes away one valence electron. Now you've got to remember that electrons are negatively charged, so it kind of makes sense that a negative charge means the addition of one valence electron. So an example here would be SO3 2-, which is a little bit different to what we just did. The one we just did was SO3. So if we do the valence electrons for this, we're going to get 6 for the sulfur, 3 times 6 for the oxygens, and then plus 2 for the negative charge, which comes out to be 26. Does anybody have any questions? The 6 is the column for sulfur and oxygen, so we're both in group 6 on the periodic table. So I go ahead now and I still do the same thing. I draw the sulfur and the oxygen, and I put in three oxygens and 3 bonds to those oxygens. And then I make the oxygens happy by giving them an extra 6 electrons, putting them in pairs like I did previously. And if I do that, I've used a total now of 24, but I have to use 26. So it's natural now for me to go ahead and put those extra 2 electrons on the sulfur. I couldn't do that before because I didn't have the extra 2 electrons to do that with. But you'll notice that in doing that, the sulfur now has 8, so it's happy, which means my Lewis dot structure is complete if I put some parentheses around it and a -2 charge to represent the 2- charge on that. And if I wanted now to look at the double bonds, there are none. And the number of lone pairs or non-bonding electron pairs, NBEP is what I'm going to abbreviate that as, non-bonding electron pairs. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 non-bonding electron pairs on that one. Does anybody have any questions? So you can see the effect of that -2. It actually added 2 electrons which went on the sulfur, which allowed me not to have to do that thing with the double bond. So again, when do you put double bonds in? If you've used up all your valence electrons and you still have something in the center that's unhappy, then you're going to need a double bond, possibly 2. Does anybody have any questions? Okay. There's another thing also in here about dative or covalent bonds as well. And a dative or covalent bond is one where 2 electrons are being donated by a single atom to create a bond. So if you've got something like BF3, because it's boron, it's got a basic, what it amounts to a space here, then it can take 2 electrons off something else to create a bond. And that bond is generally shown as an arrow from the thing that's donating the electron to the thing that's accepting the electrons. And that's actually a true bond, a true compound that will form. So that's called a coordinate covalent bond or a dative covalent bond. Does anybody have any questions about that? Okay. Well, that's it for module 12. And again, I really like doing, would really like it if some people did those soft chalk exercises. I think you'd find them quite useful. So let's look at the homework for module 12. It's not very difficult. This one is not particularly time consuming, I don't think. There's the module 12 assignment, which I think isn't very many questions. And it consists of electron configurations, then some questions about orbitals and unpaired electrons. You find that? Okay. Thank you, Morgan. I appreciate that. Then we've got lone pairs, double bonds. Yeah, not particularly difficult. If you follow what I've just done here, I think you'll find it to be a fairly easy kind of assignment. Don't forget there are videos for it too. And then we've got the practice quiz, which I think is pretty easy as well. So this one's a pretty easy points. Some people just, you definitely should do the module 12 homework because it's so easy to get to this credit quiz really. So it's pretty easy points. Some of the other ones like module 11 and module 9, and I think to a degree module 10 are a little bit harder to get to the credit stuff. So we've got the same kinds of questions really in the practice quiz as we do the assignment. But it at least lays out and shows you, this is an example of a dative covalent bond as well. And it's asking here where the dative covalent bond would be. Well, between O and B, and O would be the electron donor and B would be the electron acceptor. So that would be the answer to that one. So you can get, they're not really that difficult. All right, does anybody have any questions about module 12? Any module 12 questions? Okay. So we've got let's go back to the syllabus here and just make sure everybody understands what the story is going to be here. So we've got review on Monday, and I'm going to do a little bit of review today as well in the time we have remaining. All the homework is going to be due on Tuesday of next week, which is the 2nd of March. And the test itself will be due on the 3rd of March. There won't be class that day on the Wednesday. You do not have to wait until the Wednesday to get that test done. It can be done anytime up to that point. Does anybody have any questions? Anybody have any questions? Now, as it was with the previous test, which again, only half the people here actually did the extra credit on the test 1 in order to get that extra 5 points. And that is due the same time as the homework, but you have to get 80% on this sample module 7 to 12 test. And you need to get 80% before the homework closes. If you do that, then you can get an extra 5 points. I don't know why more people don't do it. It's absolutely crazy to me. It just shows me how many people leave things to the very last minute. So I got from that most people leave everything until the day of in order to at least half the people leave everything to the day of in order to do it, which I think is incredibly silly, but you know, I can't control that. I'd love to get an insight into why it happens, but because I can't deal with it. I don't understand why it happens. It's just completely foreign to me. But if somebody wants to talk to me about it and say, well, you know, this is the reasoning behind it, there's actually a rational reason for why I leave things to the last minute, then maybe I can get some sort of insight into that. So I'm going to do a little bit of review here. And remember, this is the test you'll actually be taking. So if you take this test often enough, let's actually, let me go back. I need to show you one other thing. Sorry about this. I'll get back to this in a second. But in the same folder, just like I had for the test 1, there's a study guide here. And the study guide will tell you the kinds of questions you're going to see for each of these questions as well, and where the modules where they come from as well. So it really lays it out. It's completely transparent. You get to see exactly what you're going to see here. So for questions 1 to 3, it's going to be conversions between grams, moles, molecules, liters of gas at STP, and you're expecting 3 questions like that. So it really does lay it out exactly what you're going to see. Nobody can come back at me and say, Dr. Musgrave, you weren't clear enough about what we were going to see on the test. Nobody can say that, especially since the actual test you're taking is the test that you should have been practicing. So when people fail, I'm really hard pressed to understand why. Generally, it's a time management issue, I think. And I know sometimes people don't understand stuff, but but if you're looking at it on the last day, you don't have time to understand it. You've got to give yourself a shot. Start it early. So for something like this is questions 1 through 3, which are conversions between grams, molecules, moles, and liters of gas at STP. You'll notice that everything's given to you up here in the equations, in the question, so you don't have to do anything about that. So if we're looking at this one, we're looking for moles. So we know it's going to be 1 mole. Actually, if you wanted, you can just do the unit first. So moles of P, and then grams of P would be on the bottom. The relationship would be 1 mole of P, and then the 30.97, which is also given in the problem as well. Then we can do a little math here. We also have to take significant figures into account. So that'd be 1.4. So let's look at that again. Looks like it's 3 significant figures. Sorry about that. That'd be 1.35 moles, or mole of P. So you know what to express it as because it says it up here. Does anybody have any questions about the first one? Okay. The next one, we're looking for liters of gas or liters of O3 at STP. So we know that we want liters of O3. So that's what I'll put down here. And grams of O3 will go on the bottom to cancel. I'm looking for a relationship between those. And it will be, according to this, 22.414 liters and the molecular weight. And the molecular weight, according to the problem, is 48.00. I'll do a little bit of math here again, and we've got 59 times 22.414, and divide that by 48, and we end up with 27.6. So that'd be 3 significant figures, 27.6, and it's going to be liters of O3. Any questions so far? Any questions? Okay, the next one. How many molecules of POCl3 does 11.50 moles represent? So we're looking for molecules of POCl3, so I'm going to write that down there first. And we have moles of POCl3 down here to cancel what we have. Then the relationship is 6.022 E23 and 1 mole. And then we can do some math here. Now in your calculator, make sure you do it pretty much the same way as I'm doing it here. And you all have the ability to do this, or should. It'd be 11.5 times 6.022, and then the EE button, 23. And there would be my answer, which would be 4 significant figures, 6.925, and then E, 24, I think. E, 24, yes, that's right. And the unit there, molecules, POCl3. Any questions? So it's sometimes what happens is people do this and they see the L there, the Cl as Ci, because in Arial, an L and a little L and a capital I kind of look the same. They actually are a little bit different, but it is difficult to see. But it's still going to be, well, you could tell it's Cl just based on the molecular weight. There's no way that could be Ci3 and it'd have that molecular weight there. So just keep that in mind, that sometimes L's and I's look alike. But if you look down here, you can see that's clearly an L when it's written in Times New Roman like that. Does anybody have any questions? Okay. So in this next one, how many atoms of Cl? So this is going to be a 2-step type situation. So I know that's what I'm looking for at the end. So for number 3, it's going to be atoms of Cl. I also know that number 2 would be grams of SOCl2. So notice how I'm not putting any numbers yet. I'm just putting in the units. I don't mind that approach. I kind of like it. But what we need here is something that links grams and atoms together and that would be molecules. So molecules, because we can link a certain quantity of molecules and atoms. So I know that up here in number 1, it's going to be molecules of SOCl2. And in number 4, to cancel that, that's going to be molecules of SOCl2 as well. Does anybody have any questions so far? Let me small. So now we need a relationship between molecules and grams, and since both of those are equal to 1 mole, and you can see it up here, molecular weight in grams is equal to 6.022 times 10 to the 23 molecules. So that goes up the top, 6.022 E23 molecules, and that equals the molecular weight, 118.96. The relationship between atoms of Cl and molecules of SOCl2, there are 2 atoms of Cl in every 1 molecule of SOCl2. Does anybody have any questions? So doing the math here, we've got 521, and that's going to be times 6. Oops, I shouldn't have put a space in there. That probably would have marked wrong. 6.022 E23 divided by 118.96 and then times 2, and that would be 5.27 times 10 to the 24th. And E24, and then that would be atoms of Cl would be the answer there. Does anybody have any questions? Any questions? Okay. The next kind of question is going to be an empirical formula problem based upon a percentage. So when doing this, it's probably best to, well, I don't think it's really possible to do it in your head. So you're really going to have to probably do some kind of table here to help you out. And I like to start here with grams and moles, and then divide by smallest. And we'll see where we go from there. So the grams are going to be the same as what the percentage is, because we're going to assume 100 grams. Then we do the moles, and the moles is going to be based around the atomic masses of antimony and nitrogen. And if you look at antimony, you go back to the periodic table here to find that. And it's 121.760. So the moles there would be 83.9 divided by, what have I got here? 121.760. And that comes out to be 0.689 on the moles of antimony. So I'm just dividing it by its molecular weight or atomic weight. And then the nitrogen, which would be 16.1 divided by 14, and that would be 1.15. So I can see the mole ratio right now is 0.689 to 1.15, which isn't that helpful to me. So I divide both through by the smallest, which means effectively 0.689 divided by 0.689 is 1. Then 1.15 divided by 0.689 is going to be 1.67. Now remember that my aim here is to get these into whole numbers, which I don't have right now. So I focus on the 0.67, and I know that that is equivalent to 2/3 as a fraction. So I will multiply by 3, which means 3 and then not 4, 5. So 1.67 times 3 would be 5, and that would be my final answer, SB3 and 5. Does anybody have any questions? Yeah. A lot of people fail that kind of question because they don't know the decimal conversions of certain fractions. Anybody have any questions? Okay. Now the next question is about an oxide. And the oxide is prepared by burning 4.00 grams of copper in air. The mass of the oxide is 4.50 grams. What's the empirical formula? Well, it's a kind of a similar problem. Whoops, I didn't mean to do that. Oh, I didn't mean to do that either. Hope I can still get to this. All right, sorry. That I didn't mean to do. Sorry about that. It's going to change my question here, but it's still okay. Here we go. So 4.00 grams of iron in air. Now, if this one, it's going to be an oxide, so that's a compound of Fe here with oxygen. So the grams of Fe will be 4.00. Now the grams of oxygen is 1.71, which is the difference between the oxide and the iron itself. This is because the oxide is everything that includes the oxygen. So if you've got the iron, then we have to take out the iron to get the oxygen in there. The biggest mistake people make is thinking that 5.71 grams is the oxygen. It isn't. It's the remainder. Does anybody have any questions? So we do the moles just like we did previously. So for that, we'll do 4 divided by 55.85. And that's 0.0716. And then for the oxygen, 1.71 divided by 16. And that would be 0.106 or 107. Now divide by the smallest. That's 1, and divide that by 0.0716. And that'd be 1.49. Now that's close to a half. So multiply both by 2, we'll get 2 and 3, so it'd be Fe2O3. Any questions? Any questions? Okay. The next one, we're looking for a percentage of water. In this case, in TiCl4.H2O. So let's see how we do that. So what you'll need is the atomic mass of Ti and chlorine and water as well for the molecular weight. Now water I know is 18.016, so I got that one memorized. But the Cl, 35.45 I think it is, but I need the Ti anyway, so I'll go back up and check that. Yeah, 35.45 on the Cl, and the Ti is 47.867. Doesn't have to be exact. It's multiple choice, so you're just going to choose the closest answer anyway. 35.45. Okay, so we're going to do a little bit of math here to come up with the molecular weight. And the formula we're using for the percentage of water is going to be 8 times the H2O molecular weight divided by the total molecular weight multiplied by 100%. So we're going to do 8 times 18.016 divided by 47.867 plus 4 times 35.45 plus 8 times 18.016. So you still include the water there as well. Remember, it's part divided by whole to get a percentage times 100. Now I'm actually not going to do the math on that. I think you can manage that. And that will, and then you choose whichever one is closest on the percentages. Does anybody have any questions about number 7? Okay. Question 8. A compound has the empirical formula NO2, molecular weight of 92. I think the best method here is to take the NO2 and find its mass, which would be 14 plus 32, which is 46. So that's what NO2 is, 46 grams per mole. The molecular weight is 92. So the molecular weight divided by what I'm calling the empirical weight is going to be 92 divided by 46. Which comes out to be 2. So 2 times 46 would be 92. So NO2, 2 times that would be N2O4. So that would be the true formula. And if you were to add that up, it should come out to be 92 as well. 2 nitrogens and 4 oxygens. Does anybody have any questions? All right, that's probably a good place to leave it. So we will continue with the fun on Monday. And remember, the test will be due on Wednesday. Homework is due on Tuesday. Probably time to get started if you haven't done so already. All right. I will see you all on Monday. Thank you.
See you Monday, Professor.
Yeah.
Oh, wait, actually,
Thank you,
Professor.
Professor.
March 3rd, we have class, correct?
March 3rd, is that the Monday?
Wednesday. That's Wednesday.
No, we don't,
No, it's
Joseph.
test. Okay.
Yeah, that's right.
Wanna make
Test
sure,
is
'cause
due.
Okay. Thank you.
All right. No worries.
Thank you. Bye.
All right. Anybody else? Alex, Jeremy? Jeremy? Okay. Yeah, so Jeremy's not there.